In the last video, we started this double pendulum problem. And what we did is we figured out, oh, we should have two degrees of freedom, or two generalized coordinates. And then we looked at our equations of constraint and said, you know what, these angles here, theta, they look like they'll be pretty useful. And then we proceeded to reason through what these things should be and write them out. So we have our x1, y1, x2, y2, all in terms of theta 1 and theta 2. Now in this video, we're going to write out our Lagrangian and see what happens. All right. So the Lagrangian, L equals T minus U. Or we could say that it equals T1 plus T2 minus U1 minus U2. Right, so we can write down a term based on each of these pendulum bobs, or each of these objects or points separately. Now let's write out T1. I keep switching between these two slightly different greens, so that's bothering me a little bit. Oh well. T1, right? Let's write it in rectangular coordinates first, right? So m over 2 times x dot squared plus y dot squared. Right, and now we can substitute these things in here. And when we do that, I'm going to skip a few steps of algebra to save time and space, and I think you'll be able to see what I've done. So if I plug this in and square it, I also plug this in and square it. So both of these things are squared. We're going to get an L1 squared out. So I'll write m over 2 and have L1 squared. And these are m1, right, the first masses. Now I can write, since we squared these individually, we have the time derivative of sine theta 1 plus, or sine squared, plus the time derivative of cosine theta 1. And really it's the derivative of negative cosine, but since we're squaring it, we don't have to worry too much about the sign. So when we take the derivatives of these things, right, I'm going to sort of just explain what I'm doing and then rewrite it. So if we take the derivative of sine, we'll get cosine, right? And then when we do the chain rule, we'll have to multiply by the derivative of theta 1 with respect to time. So that's just theta dot, or theta 1 dot, right? So we'll get a theta 1 dot with the chain rule coming out here. And we'll get the same thing here, right? So there will be a theta 1 dot coming out of these things, and then they'll both be squared. So we'll get equals m1 over 2 L squared times theta 1 dot. And then if we look at what's left in here, right, we took the derivative of sine, got cosine. So there would be a cosine squared theta here. And I forgot to write the square. Cosine squared theta 1. And then the derivative of negative cosine is sine. So plus sine squared theta 1. Right? Cosine squared plus sine squared. Does that look familiar at all? Well, turns out it's just 1. That's the Pythagorean identity for these trig functions, is one way to say it. So we can just not pay attention to this. This is just 1. Right? This is 1. So T1 doesn't look too bad, and this is actually what we got in the other video with just a single pendulum. Right, so there's T1. So I'll circle that, or put it in a box here. This is T1. So don't forget that. And now let's look at T2. T2 will end up being our most complicated looking function or piece of this Lagrangian. So T1 or T2 equals, much like this one, right? M1 over M1 over 2 times x2 dot squared plus y2 dot squared, right? So now if we substitute these in, right, these are a little bit longer, it's going to be a little bit more complicated. So let's just go at it. I'm going to show a few more steps with these ones because there's more to keep track of and more to miss. So M1 over 2, right, and I'm going to write d dt. So this is a big square bracket here. And I'm just doing this first x2 dot squared term. So this is the time derivative, so that's the dot. And then we'll do, so if we copy this, copy that here, right? And then all of this square, so we're taking the derivative of this whole thing and squaring it. And then we're adding to that, we're going to do the time derivative of all this business, all this stuff here, all of this stuff, right? Time derivative of all of that. Then I'm going to square it, and that is our T2 term. So let's simplify this. So where should we start? Well, let's just take the time derivatives. So M1 over 2. Let's take the derivative of this term. So L1 is not a function of time, so that's a constant. So if we take the derivative of sine, we get, from the chain rule, we get theta 1 dot, and then this will be the cosine of theta 1, right? And then we'll have this term here, and we'll also get a theta 2 dot out here from the chain rule, theta 2 dot, and then this will be another cosine, but of theta 2. And we're squaring all of this. All right, and now let's add this next part on. And I'll just go down the line to make sure I have room. So we'll do L1, and the derivative of cosine is negative sine, so I won't write this negative out. And we'll get a theta 1 dot from the chain rule again, and then this will be a sine theta 2, or sine theta 1. And then we'll also get this term here, a theta dot, and I forgot this 2 over here, theta dot from the chain rule, and then taking the derivative of the main function, we get sine theta 2. And we're squaring all this. All right. So let's write out these terms one at a time. So squaring this term, we'll get, well, I'll write my M1, and this should be 2. All of these M should be M2 because, right, this is the second pendulum bob, right? So I've been writing 1s when they should be 2s. So M2 over 2, right? And then let's write out these terms. So squaring this term, we'll do the square of this term, L1 squared times theta 1 dot squared, cosine squared theta 1, and then I'll square this term, plus L2 squared. I'll do theta 2 dot squared cosine squared theta 2, right? And then we'll have some cross terms, and the cross term will just be all of this stuff lumped together, plus L1 L2 theta 1 dot, and then I'm going to leave room for the other theta, do cosine theta 1, and now for the yellow, this is theta 2 dot, this is cosine theta 2, and there's a 2 out front here, right? Because there are two cross terms when we FOIL out this binomial, when we expand this binomial. So there's one of them expanded, and I'm going to continue this on this line here and say plus, right? So it'll be almost the same thing. So I'm actually going to take a shortcut, and hopefully this isn't confusing. But I'm going to copy this and paste it, right? And right, so these things look exactly the same, except one's a sine and one's a cosine. So I'm just going to erase the cosines and make them sines, and make the sines into cosines. Right, so I'm going to erase the trig functions, right, because these are so similar, it'd almost be a waste to rewrite them all. Right, same expressions except one's sine, one's cosine. So here's a cosine. I'll write a sine. Right, sine squared theta 1. And here's another cosine. I'll write a sine. So it's just sine theta 1, and then this is a cosine, so this one should be a sine. Sine squared theta 2, and then here is a sine theta 2. All right. So we have a whole bunch of stuff here, and now what we'll do is we'll simplify it a little bit more. So some of these you'll see that for the L1 squared terms, so we have L1 squared theta 1 dot squared, and then there's a cosine squared term and a sine squared term. So these add together to equal 1 times L1 squared times theta 1 dot squared. So maybe it'll be more clear if I actually write it. So M1 or M2 over 2. Almost wrote another M1. So these two terms will add, right? We can factor out this thing here, this L1 squared theta 1 dot squared, right? And then there's a cosine squared plus sine squared, which is 1. So these actually just combine into this nice smaller term here. And then the same thing happens for these L2 squared theta 2 dot squared terms. Right, so we can just write plus L2 squared, and then write theta 2 dot squared. Right, so all of this stuff here actually just simplifies into these two little guys. And now for these terms, right, these have a common factor as well, so we can write 2L1 L2 theta 1 dot theta 2 dot, and I'll copy again. I'm lazy with my writing, so I'll copy this, paste it down here, and I need another dot here. So this is plus. So we see that we have cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2. Now, and I think, yeah, maybe I should just write this out, and I'll copy and paste since that seems much faster. So copy paste. So here is that, and then and the other one is here. Copy, paste, right? And I need to make sure that everything is organized properly. All right, so it's getting better already. And now if we see that this is actually something that's a trig identity that you might be familiar with. And if you're not, I'll just rewrite it and you can see it here. So I'll just, once again, copy and paste. Copy and paste. Right? And then, but instead of this, I'm going to erase this and just write what it is after using the trig identity. So we can write the cosine, and now the color of this cosine doesn't mean much anymore because it's both, right? It's theta 1 minus theta 2, right? So it's just a much smaller way of writing this. And we can close our bracket here. So this here is our T2. So I'll put this in a box. T2. T2. Right? Here it is. All right, and if we think about this, we can sort of see where the terms come from a little bit. So the mass times L1 squared plus L1 squared times theta 1 dot squared. That's the same term, or it's very similar to the term we had with T1, right? We had this here. So we can think of it as being composed of a few parts. One of them is just the swinging of theta 1, and it has an equation similar to the equation for just the single pendulum. So here theta 1 is swinging. Here it's the same thing except it's theta 2 and L2. So this is the swinging of theta 2 by itself. You can think of it that way. And then here, this came from the cross terms, and it has both, right? It has, actually I should make this purple again so it pops out. So it actually is made of a mixture and the difference of the two angles. So this is this interaction term between the two pendulums, and it's kind of cool that we can actually sort of see the different contributions the way we might sort of think of it if we were just sort of waving our hands around and saying, well, it's kind of like both of them added together but a little different. So enough of my rambling. This is T2. And now we will find U1 and U2. So now let's look at U1 here. All right, I guess I'll just keep going down. U1. So that should equal M1 times G times Y1, right? It's just MGH. This is the potential energy of the thing. So height or Y, right? It's position in the vertical direction because gravity is in the vertical direction. So mg y1. And what is that? We can look and say that we said y1 equals negative L1 cosine theta 1. So it equals m1 g and then L1 cosine theta 1. And it's negative, right? Is that what we said? Negative cosine theta 1, right? So U2, after doing T2, U1 wasn't so bad. So here's our U1, and now let's do U2. So U2, not quite as simple as U1, but much better than T2. So U2, mg y2, and this is a 2, m2 y2. And what did we say y2 was, right? y2 is this distance here plus this distance here, right? It's the total distance down from the origin to this mass 2 here. So y2 is this function right here. So maybe I'll just copy and paste this. 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 copy, and we can go down here and paste it. And then, so this equals m2 times g times this stuff. Now with that, we have our entire Lagrangian all in terms of these angles. So let's write it out and say L equals, what did I use for L? L equals, so I'll take T2 or T1. I'm just going to copy and paste these things. That makes it much easier. Copy, right? This is our expression for T1. So this is the kinetic energy from the first pendulum, right? The upper pendulum. And then we have T2, right? So I'll copy and paste this. I have to erase some extra lines here, but copy this, paste. Maybe I'll just put it down here. I'm erasing this. Right, this is the kinetic energy from the second pendulum. Depends on the mass of the second pendulum. Right, and this is a plus. And then we're going to subtract our potential energy functions. So take this, copy, and paste it. Just trying to spare you some of the time watching me rewrite these things. Right, so this is the potential energy of the first pendulum. Right, and we should put it in parentheses. And then also minus the energy of the second pendulum, which is right here. Copy, paste. Let's erase some things here. All right, so here is our Lagrangian. It looks pretty long, right? A lot of times when you're asked to do this problem or a problem like it, you'll be told you can assume that M1 and M2 are equal, that the masses of the two pendulum bobs are the same, and that the length of the two strings or the two rods are the same. And if that were the case, then a lot of this would sort of collapse down, and a lot of these terms would combine and they squish together. But in that case, you sort of start to lose where all of these things come from, right? This is the kinetic energy of the first pendulum, right? Kinetic energy of the second pendulum, and you can see the different parts as we talked about before. The equations become less understandable even though they're shorter, I think. And in the next video, we will put this into the Euler-Lagrange formula and get our equations of motion.